Hello everyone. So welcome to this new video. In this video, we are going to have a look at autoencoders and how the encoder-decoder architecture works in autoencoder, and we will see some other aspects of autoencoder such as how it is used in generative AI applications as well. First, let us understand what an autoencoder is. So, autoencoders are typically a type of neural network that are designed to learn an efficient representation of any given data. And these are typically used for dimensionality reduction or a feature extraction techniques. So, what are the some of the unique aspects of autoencoders that makes it differentiate from other neural network architectures or models are that first, it is an unsupervised learning process in the sense that we have an input data and we train the model to recreate that input data. So there is no set output label which we are training that particular model to predict. So it is just trying to recreate that same input data by learning its representations. So, first, the basic structure of an autoencoder is that we have the input data, then we give it to the encoder. Encoder converts it into a compressed space or reduced dimension. Then we give the reduced dimension as input to the decoder, where it tries to recreate the original signal from the compressed region. Now, let us have a look at some of the unique aspects of encoder and decoder with respect to autoencoder. So, encoder usually compresses the input data into a lower dimensional space, and it represents the high dimensional data in a compact form, and it uses different layers of neural network CNN and LSTM or RNN to process the input data accordingly and allow it to learn so that the compressed region has the most useful information that can be used to reconstruct that particular input data back. Now, what does a decoder do? So, decoder generally reconstruct the compressed input back into the original signal, and how well it regenerates back the original signal from the compressed range determines the performance of the decoder. Now, what is the use of that compressed or dimensional reduction space is that a reduced dimensional representation of any input data can be used as a feature extraction technique to extract only the important features out of any given data, or we can use it for dimensionality reduction techniques similar to how we use PCA to reduce the dimension of the input data. So, for more information regarding autoencoders, you can refer to our previous video where we have gone in much deeper insight into how encoder and decoder works in general. Now, what are the loss functions that are used in an autoencoder? So, autoencoder, the main loss function is the reconstruction loss. So, it again depends on data to data. So, let us take the case of an image. So, in image, what we try to do is that we compare pixel by pixel to see how close our or the autoencoder generates the original image back, and we generally use classification metrics like binary cross entropy to verify this um, loss. In the case of an regression type signal reconstruction, we generally go for regression based laws such as mean squared error or other regression based laws to see how well the autoencoder performs, and we calculate the loss for it. So the main purpose of using the loss function again is to minimize the reconstruction error, that is make the input and the output as close as possible to each other. In autoencoder, there are again multiple subclasses or variations in autoencoder that are slightly different in the way how it is designed to work. So first we have a variational autoencoder. So what we do in variational autoencoder is that we have the input signal, we give it to the encoder. Now the encoder will compress that information. And the way we compress that information in the encoder is that we try to get the particular mean representation of the data as well as the deviation of that particular standard deviation of that particular input data. Then we perform a mathematical operation called as sampling, and we sample a latent vector out of the given compressed information. Now, for the decoder, what we do is that we give this latent vector as the input to the decoder and make it recreate the original X. So, by doing so, we are making sure that representation of data in the compressed format follows a certain uh, pattern or distribution, and we add an additional loss term in the case of variational autoencoders known as scale divergence loss to check the if the distribution of data in that compressed region remains same. So these type of models are generally uh, called as probabilistic model because we add a probabilistic constraint to the compressed region. So the advantage of using variational autoencoder is that it enables generating new and similar data from the compressed region rather than recreate just the original data. So let us take our previous example of compressing that image of 4 and recreating that image of 4. So when we train a normal autoencoder, what we do is that we try to minimize the loss, and by doing so we try to recreate the exact image of 4 again. But in the case of variational autoencoder, we can once it finished training, we can use it to generate different variations of 4 images as output also. That way we have some generative capability we try to get out of that particular model because of the probabilistic constraint of that uh, compressed region. Next, we go for the denoising autoencoders. So these type of autoencoders are generally designed to remove noise from the input data and try to recreate the noiseless input data as the output. Next, we have sparse autoencoder. So this main purpose of this autoencoder is to create sparsity in the latent space, and these autoencoders generally used for feature extraction techniques where we have only a few latent variables. Now, where are autoencoders generally used in generative AI applications? First is image generation. So first subclass of image generation which we are generally where the autoencoders are used is style transfer. So let us say I have an particular image that is painted in a particular style. Now let us say I want to change that painting or image into a different format or style of painting. Then if I have an autoencoder that is designed to do this particular task, then I can easily use that particular autoencoder to change the style of an image to that new style. Next task where generally autoencoders are used is in a called as super resolution, where we have a low resolution picture and the similar to how the denoising autoencoder removes the noise, this autoencoder is supposed to or is designed to make that image much more in a high resolution format. That is, we have more square pixels per inch, so that the image looks much more very clear. Next, we have some very limited use cases for autoencoders in generating new text sequence. But with the introduction of transformers, this aspect of autoencoders are not that comparable compared to the transformer models. Next, they use autoencoders for anomaly detection. So let us say we have a trend that is being followed and we want to detect all the outliers in a particular input data. We can design an autoencoder to do this particular task. Now, what are the key advantages of using the autoencoder? First, it is an unsupervised learning. So we don't have to label that data and spend lot of time labeling the huge data sets. Next, we get a compressed data. So by doing so, we are giving that compressed information of any particular input data that can be used for a downstream task also. Say, for example, if we again take the case of same for image, when we give it to the encoder, we get the compressed uh, dimension of that for image, and that compressed dimension can be used as to train a particular classifier model to classify different digits, say from 0 to 9. And by doing so, we are not giving the entire images input to the classifier, but an extracted feature of those images as to the classifier. And by doing so, the classifier can get higher accuracies for such downstream task. Next, VAEs, or the variational autoencoders, are finding more and more applications similar to style transfer and um, a super resolution task, and much more newer task where variational autoencoders are being preferred. Next, we discuss some of the limitations of autoencoder. So in training an autoencoder, when compressing that information, though we are getting all the important features, there is a loss of information when doing so, and this can sometimes really affect either the reconstruction or using that compressed information for the downstream task. Next, we have a high chance of overfitting, since we are just trying to recreate that original input image. The models can sometimes easily overfit if we do not have the right amount of data or the right quality of data where the model can generalize much better. And as I've discussed earlier, it is not ideal for all generative AI tasks, but rather very limited use cases. So where are such variational autoencoders being used in different industries? So let us say take the healthcare industry, where the autoencoders are generally used for anomaly detection in medical images, such as detecting tumor in MRI scans. Next, in the case of creative industries such as music, filmmaking, or YouTube, we can use autoencoders to generate new music, artworks, or designs. And in the case of natural language processing, we have a very limited application of text generation or sentiment analysis using variational autoencoders. Next, we have a use it in AI industry as well, where we use autoencoders as a data augmentation tool to generate similar data to input data that we can then use to train our model, that is not autoencoders but the main model which we are intending to try. But because of lack of input data, the model was not able to generalize well, so we used autoencoders to generate similar images but not exact same input image, and using the newly generated images and the old one to train the model. So in conclusion, autoencoders are acting as a fundamental tool for learning effective data representation. And VAE, or the variational autoencoders in general, have uh, given more uh, useful use cases to the autoencoder class, whereby it is being used in some generative AI applications as well. And as research progresses in autoencoder and different variations of the same autoencoders come up, it is finding new and newer applications in the generative AI task as well. So that is it for this particular video. So if you have any questions, or do you have any doubts regarding the autoencoder, feel free to contact us. And do also make sure to follow us on our socials. And if you have liked this video, please don't forget to like, share, and subscribe.